Hi everyone, I am Dr. Sharada, Assistant Professor in Mallareddy Engineering College for Women, Hyderabad. Today we are discussing about a transformer. First of all, what is the need of a transformer? In most cases, appliances are manufactured to work under some specific voltages. Transformers are used to adjust the voltages to a proper level. The transformers are a basic components of the transmission of the electricity. Transformer is used to increase the voltage at the power generating station and used to decrease the voltage for household purpose. By increasing the voltage, the loss of the electricity in the transmission purpose is minimized. What is a transformer? Transformer is a static device. It transfers the electrical energy from one part of the electrical circuit to the other part of the circuit without changing the frequency and with the desired change in the voltage or current. The basic principle of a transformer is Faraday's laws of electromagnetic induction, and it is also called mutual induction between two coils. A transformer used to increase the voltage is called a step-up transformer, and the transformer used to decrease the voltage level is called a step-down transformer. Working principle of a transformer. The transformer works on the Faraday's laws of electromagnetic induction. According to mutual induction principle, when two coils are inductively coupled and if one coil current is changing uniformly, then an EMF is induced in the second coil. This EMF can drive a current when a closed path is provided to it. The winding which is connected to the supply is called primary winding, and the winding which is connected to the load is called secondary winding. It produces self-induced EMF in primary winding and mutual induced EMF in the secondary winding. When primary winding is connected to a source of alternating voltage, an alternating magnetic flux is produced around the winding. The core provides magnetic path for the flux to get linked with the secondary winding. Most of the flux gets linked with the secondary winding, which is called as useful flux or main flux. And the flux which does not get linked with the secondary winding is called as leakage flux. As the flux produced is alternating, EMF gets induced in the secondary winding according to the Faraday's laws of electromagnetic induction. This EMF is called mutually induced EMF, and the frequency of mutually induced EMF is same as that of supplied EMF. Physically, there is no electrical connection between two coils, but they are magnetically connected. The induced EMF in primary and secondary windings depends upon the rate of change of flux linkage, that is n d phi by dt. d phi by dt is change of flux and is same for both primary and secondary windings. The induced EMF in primary winding is proportional to the number of turns N1. Similarly, induced EMF in the secondary winding is proportional to the number of turns N2. Basis of winding. Step-up transformer. The number of windings on primary side is less than the number of windings on the secondary side. That is, NP is less than NS. Step-down transformer. The number of windings on primary side are more than the number of windings on secondary side. That is, NP is greater than NS. For isolation transformer, number of windings on primary side is equal to number of windings on the secondary side. The same we can observe from the diagram also. For step-up transformer, the primary side windings are less compared to the secondary side windings. For step-down transformer, the primary side windings are more compared to the secondary side. For isolation transformer, primary and secondary side both are equal. Transformer classification. According to the number of phases, transformers are classified into single-phase transformers, three-phase transformers. According to the construction, the transformers are classified into core-type transformer, shell-type transformer, berry-type transformer. According to the function, the transformers are classified into power transformer, step-up transformer, step-down transformer, distribution transformer, instrument transformer, current transformer, and potential transformer. Special purpose transformers are spot connection transformers, V connection transformers, pulse transformers, auto transformers, welding transformers. According to the type of cooling, transformers are classified into air-cooled transformers, oil-cooled transformers. According to the location, the transformers are classified into indoor transformers and outdoor transformers. According to the frequency, the transformers are classified into low frequency transformers and high frequency transformers. According to the rating, the transformers are classified into low rating transformers, medium rating transformers, and high rating transformers. EMF equation of a transformer. When the primary winding is excited by an alternating voltage V1, this is V1, it circulates alternating current, produces an alternating flux phi. This is the flux phi. The primary winding has number of turns N1. The alternating flux phi linking with the primary winding itself induces an EMF in it, and it is denoted by E1. This is E1. The flux links with the secondary winding through the common magnetic core. This flux links with the secondary winding through the magnetic core. It produces induced EMF E2 in the secondary winding. This is the E2. And this is mutually induced EMF. Let us derive the equation E1 and E2. The primary winding is excited by purely sinusoidal alternating voltage. Hence, the flux produced is also sinusoidal in nature, having maximum value of phi max, and it is shown in the waveform. This is the sinusoidal waveform of the flux, and we have the maximum flux at T by 4F time. The phi is the flux and phi m is the maximum value of the flux. N1 is the number of primary winding turns. N2 is the number of secondary winding turns. F is the frequency of the supply. E1 is the RMS value of the primary induced EMF. E2 is the RMS value of the secondary induced EMF. From Faraday's laws of electromagnetic induction, the voltage EMF induced in each turn is proportional to the average rate of change of flux. Therefore, average EMF per turn is equal to average rate of change of flux. Average EMF per turn is equal to d phi by dt, where d phi by dt is the change in flux by time required for change in flux. Consider the 1/4th cycle of the flux as shown in the figure. Complete one cycle gets completed in t is equal to 1 by f seconds. In 1/4th time period, the change in flux is 0 to phi m. So d phi by dt is equal to phi m minus 0 by 1 by 4f. The average EMF per turn is equal to 4f phi m volts. As the flux is sinusoidal, the induced EMF in each turn of both the windings is also a sinusoidal in nature. For sinusoidal quantity, the form factor is equal to RMS value by average value, and it is equal to 1.11. Therefore, RMS value of induced EMF per turn is equal to 1.11 into 4 into F into phi m. That is equal to 4.44 F phi m. There are number of primary turns, hence the RMS value of induced EMF on primary is denoted by E1 is equal to N1 into 4.44 F phi m volts. While as there are number of secondary turns, RMS value of induced EMF on secondary denoted is E2 is N2 into 4.44 F 5M volts. Therefore, E1 is equal to 4.44 F 5M N1. E2 is equal to 4.44 F 5M N2 volts. Here 5M is equal to Bm into A. Bm is the flux density, A is the cross section area. Voltage and current transformation ratio. E1 is equal to 4.44 F 5M N1. E2 is equal to 4.44 F 5M N2. Transformation ratio K is equal to N2 by N1 is equal to V2 by V1 is equal to E2 by E1 is equal to I1 by I2. N2 is the secondary side number of turns. N1 is the primary side number of turns. V2 is the secondary side terminal voltage. V1 is the primary side terminal voltage. E2 is the secondary side induced EMF. E1 is the primary side induced EMF. I1 is the primary current. I2 is the secondary current. For a step-up transformer, N2 is greater than N1, E2 is greater than E1, K is greater than 1. For a step-down transformer, N2 is less than N1, E2 is less than E1, K is less than 1. For isolation transformer, N2 is equal to N1, E2 is equal to E1 and K is equal to 1. Equivalent resistance of a transformer referred to primary and secondary. This is the equivalent resistance of a transformer having primary side and the secondary side. R1 is the primary winding resistance. X1 is the primary winding reactance. This is the R1 and X1. Similarly, R2 is the secondary winding resistance. X2 is the secondary winding reactance. E1 is the primary induced EMF. E2 is the secondary induced EMF. V1 is the primary terminal voltage. V2 is the secondary terminal voltage. Here I0 is the no load current. Im is the magnetizing component of no load current. Iw is the working component of no load current. I2 is the load component of primary current. I1 is the primary current. I2 is the secondary current. And ZL is the load. This is the equivalent circuit of a transformer referred to primary side. In this one, the secondary side resistance and reactances are shifted to primary side and those values are R2 dash and X2 dash respectively. This R2 dash is equal to R2 by K square and X2 dash is equal to X2 by K square, where K is the transformation ratio. Z2 dash is equal to Z2 by K square. The equivalent resistance referred to primary side is equal to R01 equal to R1 plus R2 dash is equal to R1 plus R2 by K square. Similarly, X01 is equal to X1 plus X2 dash is equal to X1 plus X2 by K square. Z01 is equal to R01 whole square plus X01 whole square under root. This is the impedance referred to primary side. This is the equivalent circuit of a transformer referred to the secondary side. In this one, primary side resistance and reactances are shifted to secondary side and those values are R1 dash and X1 dash. R1 dash is equal to K square into R1. X1 dash is equal to K square into X1. Z1 dash is equal to K square into Z1. The equivalent resistance referred to secondary side is equal to R2 plus R1 dash, that is equal to R2 plus K square R1. Similarly, X02 is equal to X2 plus X1 dash, that is equal to X2 plus K square X1. Z02 is equal to R02 square plus X02 square under root. This is the impedance referred to the secondary side. Efficiency of a transformer. Efficiency is equal to output power by input power. Output power is equal to V2I2 cos phi 2 by V2I2 cos phi 2 plus core losses plus copper losses. V2I2 cos phi 2 by V2I2 cos phi 2 plus iron losses are indicated by Pi. It is also called core losses, and copper losses are indicated by Pc. Here iron losses are constant, but copper losses are is nothing but I square R losses. So I1 square R1 plus I2 square R2. Efficiency referred to secondary side V2I2 cos phi 2 by V2I2 cos phi 2 plus Pi plus I2 square or not 2. Or efficiency referred to primary side is equal to V2I2 cos phi 2 by V2I2 cos phi 2 plus Pi plus I1 square or not 1. Working of the three-phase transformer. In three-phase transformer, three cores are arranged at an angle of 120 degrees to each other. When the primary is excited with the three-phase supply source, the currents IR, IY, IB start flowing through the individual phase windings. These currents produces the magnetic flux phi R, phi Y, phi B in the respective cores. In three-phase system, at any instant, the vector sum of all the currents is 0. In turn, at the instant, the sum of all the fluxes is same. These fluxes induce the secondary EMFs in respective phases such that they maintain their phase angle between them. This is the three-phase transformer, and these three cores are displaced by 120 degrees each other, and this is the three-phase supply R, Y, B. These three-phase transformers are connected either in star-star connection, delta-delta connection, star-delta connection, or delta-star connection. These are the voltage and current relations between different connections. Finally, in case of star connection, the line voltage is equal to root 3 into phase voltage and line current is equal to phase current. In delta connection, line voltage is equal to phase voltage and the line current is equal to root 3 into phase current. This is the summary. Thank you.